You type kubecontrol get pods, hit enter, and expect a clean list of data. Instead, the connection slams into an authorization blockade. Beneath that simple terminal command is a rigid cryptographic routing engine constantly analyzing your request. This dense, interconnected routing graph is your Kubeconfig file. It operates as the master blueprint, dictating exactly how that routing engine behaves. We are going to deconstruct this system by building a zero-trust development context entirely from first principles. Grasping this architecture replaces the practice of blindly guessing at permission errors with the ability to diagnose them based on the underlying structural logic. This hub-and-spoke model shows the context acting as the primary gatekeeper. Before the Kubernetes API server even evaluates an access policy, it processes this context. The context relies on 3 variables. The first is the cluster. This defines the target compute destination and holds the server's public certificate to verify its identity. The second variable is the user. This establishes exactly who is connecting to the server, verified by a cryptographic token. The third variable is the namespace. This acts as the default logical boundary, constraining the connection to a specific operational area. If any piece of this triad is misaligned or missing, Kubernetes drops the connection immediately. It will not even look at your role permissions. To provide access for an external developer, we first need to create a highly constrained identity. We execute a command to generate a new service account named devuser, placing it entirely inside the dev team namespace. Identity inside Kubernetes requires cryptography, which means this service account needs a specific authentication token to function. This flow diagram tracks a secure token forged inside the cluster, then extracted to our local terminal. Using set credentials, we inject this token into our local configuration. Finally, we bind the user, cluster, and namespace to activate a new context pathway. The local file now recognizes the devuser entity perfectly, but if we attempt to run a command, it fails. This recognized identity still has absolutely zero access to perform actions. An authenticated identity without explicit authorization is effectively powerless in a zero-trust architecture. Role-based access control provides the mandatory bridge connecting an identity to a permitted action. This matrix table breaks down the construction of a role, pairing explicit verbs like get, list, watch, create, and delete directly to the pod's API resource. We execute a role binding, which fuses our devuser service account directly to this role. A common operational error occurs here. Developers use the -- dry run flag to generate local YAML configurations, but fail to apply them to the cluster. A missing role binding on the server results in an immediate forbidden denial, even if the local YAML is perfect. Running the apply command is what actually synchronizes your local intent with the API server's reality. With the rules applied, the administrator officially switches the active terminal context to this newly authorized user. Under this new identity, basic pod listing commands now successfully return data. RBAC acts as the exclusive translator, turning a cryptographically verified user into a permitted actor within their defined namespace. This terminal displays the developer attempting a standard kubectl logs command, only to be unexpectedly blocked. Why does an identity with explicit access to create and delete pods get rejected when simply trying to read their logs? The Kubernetes API enforces extreme granular isolation. It is a common misconception that logs are just a child attribute that comes bundled with a pod. This branching API tree shows pod/log as a completely distinct, isolated sub-resource. The API server scans the role and finds a mismatch. The user has permissions for pods, but not the log pathway. Appending pod/log into the role matrix turns the locked gate green. Upon reapplying the role, the terminal immediately returns the desired log data. The system assumes nothing. If a sub-resource is not explicitly hard-coded into the matrix, access is structurally impossible. Consider the Kubernetes administrator tasked with debugging these RBAC failures. The traditional debugging method is to permanently switch your local context, fully adopting the user's constraints. But remaining elevated in a root context while trying to guess user permission failures introduces heavy operational risk. This diagram models API impersonation using the -as user flag. It provides a surgical alternative to a hard context switch. Impersonation allows the admin to test the RBAC matrix accurately without ever altering their underlying master kubeconfig. This prevents dangerous privilege probing, allowing teams to validate least privilege security without exposing the root system. We started with a blank kubeconfig and built a precise, tightly sandboxed cluster environment. This requires a flawless pipeline, the context triad, the role binding bridge, and explicit sub-resource definitions. Mastering these isolated mechanics changes the kubeconfig from a fragile file into a reliable tool for cluster governance. In high-stakes environments, relying on broad assumptions rather than explicit cryptographic architecture is the fastest path to system failure.